Good morning. Welcome to my short discussion about LLVMClang and ARM 32-bit. So this is kind of a private project of me. I did that since on and off since maybe about 4 years. And yeah, I quickly go through what I did. So just maybe step back, compiling the kernel with LLVMClang. What does it mean? So the nice thing with LLVMClang is it's kind of a cross-compiler by default because it has multiple backends, and you can actually see which backends are enabled using LLC-version. So most configuration, they have LLVMClang configured to generate code for multiple backends. Currently, to build the kernel, you still need a GNU cross-compiler toolchain because not everything can be done using LLVMClang currently. So the assembler and linker is still required from the GNU cross-compile toolchain. And how do you do it? You set up an environment as usual to do cross-compiling, like export arch equals ARM, and set your cross-compiler prefix there. Also, your cross-compiler needs to be in the path, of course, so that it can be found. And then you can compile using regular commands. You just need to set cc, so the compiler to Clang, and host cc to Clang too. And what is new since V418, the compiler detection has been moved to the kconfig phase, to the configuration phase of the kernel. That means that you really need to actually set Clang as your compiler already at configuration time. Otherwise, it will pick up GCC, and then you have a configuration which is not compatible with what you do when you compile. So just when you do defconfig and do nconfig or menu config or whatever you are using, you need to set Clang already. And what I noticed when I used GCC toolchain, which was outside of like the regular directory, like user bin, I used usually the Linaro toolchain, the precompiled one, and stored it in my home directory. If I did that, then Clang wasn't able to really find that toolchain. And what then usually happened is that it falled back to use the GNU assembler and linker, which of course failed. There's a simple workaround, just assuming Clang into that cross-compiler toolchain, because Clang seems to search the path it is executed from. And we also have a fix upstream in the makefile, which basically tells tells Clang to use GCC from the GCC toolchain directory. So that should be fixed in 420. It's not a problem if your compiler and your if the GNU cross-compile toolchain is in user bin and LLVMClang, then it works fine. So if you use everything from the distro, then that works. Yeah, and short brief history. So where does LLVMClang support kind of got worked on? It was a Linux Foundation project in 2012 to 2014. Bihan Webster and others worked quite a bit back then. It got then a little bit forgotten, or yeah, nobody worked for a while, or only on and off. And I also back then rebased just the remaining patches which were not upstream from time to time, and submitted mostly fixes which were kind of which Clang kind of reported, so like warnings or other issues. And since 2017, also the Google Android team pushed to upstream kernel patches to support Clang. They used Clang, LLVMClang for Android since 2010, but at 2017 they kind of came to also really use it for the kernel. So there are also some good resources there. They have the LTS branches and maintain basically a patch set to also build those LTS branches using LLVMClang. Yeah, and in 2017, I pushed a bit more build errors and fixes which were necessary to build ARM32. And in 2018, I had then, it was only like 5 patches which were missing to really build ARM32-bit with LLVMClang upstream. And they got merged in v4.18. So v4.18 compiles fine, just upstream. There's one remaining issue. I come to that later. So why? Well, I guess most of you know about LLVM and Clang. It has good error and warning reportings, and already the competition is just a good thing to have, right? And so for me personally, it's kind of a just interesting project to work on, but I actually also had a real-world kind of issue which got fixed by just using Clang. So I work for a company and we do ARM embedded modules. We do Tegra modules, and Tegra 124, that's actually Tegra TK1. And my friend actually said, well, he has the module and he tried using mainline and used some random graphics application, and it just crashed. And he didn't bother. I mean, it was just he played something around, like, why is it crashing? That doesn't make sense. It shouldn't crash. Well, I don't have time to look into it. And then later, the same week, I compiled with Clang, and that warning showed up that this variable here is not used. And this variable is actually used in array length to initialize a structure, but GCC doesn't print an error warning in that case, but Clang does. And it was an obvious issue in the code. So I fixed that obvious issues and did upstream, and my friend then the other week came and said, oh, you fixed my issue. And I'm like, oh, that was not really intentionally. But yeah, it was a real-world issue which just got fixed by compiling with Clang and looking at those warnings. And I came across several warnings which were probably really bugs. It's sometimes hard to tell whether it's a real-world bug, but this one was really a real-world bug, definitely. So yeah, v4.18, that's the current state. Multi-v7dev config without config efi works. So that will work with v4.20. There's a patch already to also fix the efi issue. So with 4.20, we should have multi-v7dev config compiled by default. There was a small mishap in 4.19 RC1. Some other work on the compiler headers broke actually ARM32 again. So yeah, and I noticed it, and we then made sure that those patches still make it into 4.19, so that we also have 4.19 still working. So yeah, that's currently a little bit the issue, because nobody really uses, or I heard we just start to kind of use CI to actually compile also with Clang regularly, so that these things get noticed quickly. Yeah, and what is known to not work? So there's still quite some things we can do. I mean, what I noticed is function tracing actually fails to link, even. But that one I got fixed, that it links, but then it crashes at boot. And it seems that so function tracing uses this mcount ABI, and that seems to be different between GCC and LLVM for ARM32. I'm not sure whether that should be the case. So yeah, there's an issue tracker on GitHub where I put the information I have so far, and yeah, that needs further work. Then ARMv6 fails to build currently. So it first fails to kind of detect ARMv6, but if you get around that, then it actually shows you that it emits the wrong CPU. And then the assembler doesn't know that CPU. And that seems to be an LLVMClang issue. I think I haven't tested it. There are patches almost on the way, so I think we got that fixed pretty soon. Would then, of course, need a newer Clang version. Maybe we want to have something in the kernel to kind of fix it from the kernel side for older Clangs, or we just don't care, I don't know. Well, there are certainly some features which are known to not work, or yeah, we could now also add something in kconfig to easily kind of disable those functions so that the other functions or kernel configurations which are known to not work, that they don't break. ARMv5 will probably never work. There's no backend for that for LLVMClang. We probably also don't care, so we could just make sure that the user cannot select this configuration. Frame pointer based stack unwinding, that probably won't work too. Yeah, now that we have kconfig symbols for the compiler, it's actually really easy to kind of make at config time sure that options which are not supported by the kernel don't even get enabled. So that helps quite a bit for the LLVMClang use case to kind of yeah, make sure that configurations which can't work with LLVMClang, that they are not even configurable. User integrated assembler. It needs ARM unified syntax. I'm not sure how far we are there. I think several worked on that also a little bit, but it's not upstream. And then, of course, there's a lot of things we probably could do in terms of using static analysis tools and so on. I haven't really looked into that. I just tried to make ARM 32-bit upstream working, but yeah, there's certainly a lot of things we could do there too. Yeah? Yeah, this is a small slide. What I usually use to kind of debug the issues, just if you want to play with Clang 2, it's kind of, these commands are usually helpful to get to the bottom of issues you're seeing. Yeah, now, I don't know, would like to open the discussions if anybody has other kind of points or what you feel. I mean, ARM32 is to some degree not, I mean, it's not the most important architecture at that point for most of you, I guess, but I feel it's still interesting and still work worth doing. I'm not sure where we should kind of put focus on and so on.
I understand the use of Clang to compile Linux kernel for investigation purposes, to get the additional warnings, to use static analysis tools. But is there interest to actually run kernels in production compiled with Clang?
So from my side, we don't do it. I don't see a lot of value for us now. As we're actually a rather small company and using computer on modules. But I mean, I guess there are certainly use cases where it makes sense.
The main reason that I can see are the Android builds. If people are using the Android SDK, there is a somewhat recent LLVM in there. And there are two known broken versions of GCC that are several years older. They have known bugs, they produce incorrect code, and that's what people use to build Android kernels today. That's not ideal. Yeah, so I don't think they will upgrade the GCC.
So yeah, that's valuable for the kernel community. If the Android folks use LLVMClang, then we can get rid of those older GCC versions.
Yeah, so I have a short remark. At least on the ARM64 side, we get a lot of requests from the Google guys and also the LLVM community to support LLVM, supporting the compilation of the kernel using LLVM. One of the issues which you've outlined is that there's a significant departure in terms of supported features between LLVM and GCC, the lack of 1176 support, for example. On the ARM64 side, we've seen all kind of things such as assembler constraint not being supported, the compiler just erroring out. Is there any effort that is done to track these differences and to track whether or not they are being resolved? Because I can't see myself deciding to support LLVM as a primary compiler for the kernel if it's still always lagging behind. I want to have a known working version of LLVM. And at that point, from that point on, I can guarantee that it won't break.
Yeah, I guess, I mean, the upstream kernel definitely accepts any patches. And as I have seen also Greg, he basically considered that breakage of ARM32-bit with Clang as a regression. So there's definitely willingness in the kernel community to support that fully, right? But when if it
goes both ways. It's also having the LLVM folks making sure they support everything we come to rely on.
Yeah, I was earlier this week in a talk at the toolchain group, and I mean there's also work on making sure that they compile regularly the LLVM toolchain and so master LLVM Clang toolchain and master kernel and kind of track regressions. So I mean, we go steps, right? So first, we have now a state which works with certain limitations on certain conditions. We try to certainly retain that state. I mean, don't do regressions on any of this combination, but also go forward and just
so at the moment, so Mark tested the latest release of LLVM. You still can't compile an ARM64 kernel.
Okay.
That is incorrect.
You cannot compile a defconfig ARM64 kernel using the 7.00 binary release of Clang from LLVM.org, as it does not support the call-saved options used for the LSE atomics. You may be able to use it without that, but that is not a defconfig upstream ARM64 kernel which needs to function.
Yes, correct. So defconfig minus one option.
Yeah, that's where I am at, right?
Yeah, there has been some movement on that recently. It won't have reached, won't reach 7. I think that certainly the fixed version, I think, was merged a few days ago. And I just noticed that I think that some of the caller-saved ones might have gone in as of in the past few days, something like that. So I think there is certainly an effort to get those fixed. As opposed to, I guess, supporting everything, there is I think, a strong effort within at least some parts of the LLVM community to make this work. I guess the difficult bit is when you end up with something that will be very difficult to support within LLVM, either because of the way it's structured or the way it will impact other tools. And I guess that's the bit where we've got to get both ways, where can we do whatever's reasonable or as quickly as possible, but there may be some bits where we'll struggle a bit at that side.
So what I noticed is that a lot of the bugs you showed where things don't quite work while building the kernel, like ARMv6, Big Endian, and those things, it's really just that nobody has ever tried that, because building the kernel, we do something that's slightly different than building user space, and you can build an ARMv6 Big Endian user space application just fine. It's just that the kernel happens to do something just slightly different where we need a one-line change in Clang and nobody has bothered to fix it. So it's the problem here is the lack of existing users. So once we get more people to use it, then it will work. Aside from that, there's a completely separate thing where we have large features missing in Clang that will take a lot of time to implement.
Yeah, and I agree. I mean, sometimes it can be a very simple change in the kernel that will make it perfectly fine to compile with both GCC and LLVM, and we're completely happy to entertain that.
Yes.
It's
Or a tiny change in Clang, one or the other.
yeah, but it's when sometimes we have difficult conversations where I hear things like, "Oh no, you can't use that feature," which means that gates as something like a security fix, and I can't get that merged because LLVM won't compile.
Yep.
And that's where there's a bit of a disconnect, and I'd like to make sure we resolve that in a more constructive way.
So we can compile some kernels with Clang. Do they boot?
Yes, yeah, yeah. So I did also boot testing, yeah. ftrace, that was actually the only one. So after I fixed the linker, I'm like, hooray, and then boot. No. So there's really a fix, an issue which breaks booting them. But other than that, if I disable function trace and disable EFI, build a kernel, I can boot that on real hardware just fine.
Just check, have you tried booting with KVM at all? Because we had issues on ARM64 where that did not work. with
I
Clang.
think I did it once with QEMU, yeah. I'm really not sure 100%.
Okay.
I need to
No worries.
check.
So, have you compared the binary sizes of compiled with LLVM and compiled with GCC for 32-bit? I mean, do you have some improvements?
Well, I compared sometimes things just like single object files doing disassembly just when tracking issues, but not like on an overall kind of where we go.
One of the projects which I am working on, Tiny Linux, our main interest is to reduce the binary sizes. And I mean, so we are kind of looking for, even I tried for LLVM instead of GCC just to get as much optimization as possible. So I'm just curious about that thing. Like in Tiny Linux, we may use LLVM rather than using GCC if we get better results.
Yeah, I really haven't done work on this.
I think that ftrace program is that the function prolog will not same in GCC and so C Clang, so that it just check that the branch to the M count, but it expected some fixed offset from the function entry. So yeah, I think we can configure that.
Yeah.
And I have a question about the compilation and the linking. If we use a Clang, the link process is parallelized or still single?
Well, because we still use the GNU cross-compile toolchain to link, it's still single-threaded. So, but once we would go there to use also Clang in LLVM toolchain for that, then of course it would be multi-threaded. But I think that's that's certainly a situation where we are a bit further away from. Maybe Peter.
In some ways, the link is an orthogonal problem. You could stick with GCC and get, I think there was a patch to make GCC able to use LLD with fuse LD equals LLD, but I don't know whether it ever got merged. But in theory, that's a one-liner if it happens. So I guess if you wanted the multi-threading linking of LLD, there would be a long debugging process of working out where things didn't quite work. But I think that would be an orthogonal project to Clang, I think.
Maybe also to the issue tracking. So that's actually that GitHub project here, Clang built Linux, that some Google folks started that project. And yeah, if you're interested in this work, I definitely can recommend looking in there. There's quite some issues now tracked, and it gets updated daily basically to get things kind of fixed, because it's kind of an issue it can be an issue on both sides. It's kind of nice to have this issue tracking in between, where we then link to like kernel mailing list discussions or bugs in the LLVM bug tracker. Yeah, I think time's up, maybe.
I think it's lunchtime anyway, so maybe we can have a few more minutes. So I have 2 more things. So I'm trying to work towards 0 warnings. I'm not completely sure how I want to do this. I have gotten there eventually with GCC, and there was a lot of work. I would like to see Clang get there too, both on 32 and 64-bit. And the other thing is it's important to remember that there are a lot of optimizations that Clang will not do, where we rely on GCC to do certain things for us in the kernel that Clang just does not implement. There are a couple of examples for those. So kernels built with Clang are likely to run slower in a number of micro benchmarks than kernels built with GCC.
Yeah, I've noticed that too. For instance, the RAID algorithms, they get benchmarked at the beginning, and you see it quite clearly that the LLVM ones are currently quite a bit slower. But that's really because there's GCC-specific code, or in the makefile there are GCC-specific optimizations being done, and like loop unrolling enabled or something like that. And that's not being done for Clang, so yeah, obviously it will be slower.
Okay, it depends on optimization level, but Clang does a loop unrolling I think at the show 3 by default. So it's just that GC doesn't do it by default.
Yeah. Yeah, but I think also Clang in that particular situation, it cannot reason really what it's going to be, so it doesn't do the unrolling. And how kind of GCC, or how we worked around in GCC, we forced unrolling at that point, and that's not being done with Clang.
Another point to watch out in the difference of compiler optimizations is that GCC enables vectorization only at dash 3. It doesn't enable it at dash 2, and I think the kernel is being compiled with dash 2, while Clang does enable vectorization at dash 2.
Okay. So it could be faster in other benchmarks, I guess.
Potentially, yes.
Yeah. Yeah. With regards to warning, I usually kind of track or try to fix warnings, especially if they are kind of look like bugs. But yeah, a lot of warnings are just warnings, and then it's a bit harder. But I was thinking there, like some warnings, I think we could also enable them in GCC, not like the enum conversation warning. Is that not also available in GCC? Because if you would enable, there's the disconnect a little bit. With LLVMClang, we have them enabled by default, but with GCC, I guess if we could enable it too there, the enum conversation conversion. Like if you have 2 different types enums, so Clang doesn't warn if you just assign it. Yeah, okay, that's, yeah. So yeah, things need to get fixed first. Yeah. Okay, thanks.